So yeah, good morning, good afternoon, everyone. My name is Andrea Auconi. I'm a researcher at Ca' Foscari University of Venice in Italy. And yeah, today I will talk a bit about non-equilibrium steady states and of the Fokker-Planck equation, and in particular, how relaxation properties are related to the entropy production at steady state, what in a previous talk has been referred to as the housekeeping entropy production. Okay, let me just, to set the stage, introduce the Fokker-Planck equation, which is a continuity equation in terms of the probability currents, P times nu, where nu is the local mean velocity, which is decomposed into drift and diffusion terms. Okay, now if we assume the existence of a steady-state distribution, meaning a distribution function such that the time evolution operator does not change it, then this separates our systems in two classes, the equilibrium and the non-equilibrium steady states. The equilibrium, for which detailed balance is respected, and the non-equilibrium systems for which currents are still present at the steady states. Okay, here we got two prototypical examples in two dimensions. On the left, we have a linear system, an Einstein-Uhlenbeck process, while on the right, we have a quadratic potential. Of course, more general examples are possible. Here, the background color represents the density, and the arrows represent the probability currents. Okay, a key definition which is seen over and over, quite important here, is the irreversible entropy production rate, which is here expressed in terms of the local mean velocities, squared local mean velocities, and we know this is equal to thermodynamic dissipation when a sign relation holds. Another important definition for this talk in particular is the corresponding equilibrium steady state. That means that steady state, which has the same density as the non-equilibrium system that we are studying, but that has zero currents, and this can be implemented by switching the force to this equilibrium force, which comes as a gradient over potential minus TLMP. Okay, now to introduce the motivation of my study. The motivation is this question: can we estimate the steady-state entropy production when currents are not observable? And it's not only currents, let's say that also microscopic trajectories are not observable and also not partially observable, so that really we have to we cannot apply the thermodynamic uncertainty relation. And a possible answer that has emerged from the community in various papers, here I've put just three, is to look at the density relaxation dynamics. In particular, reference 4 looks at non-reversible samplers, means the problem of sampling a probability distribution, and they have observed, along with many other researchers, the fact that adding non-equilibrium currents to these samplers, it speeds up this optimization problem, the convergence of the algorithms. Then in reference 5, they studied this connection for the master equation, basically how relaxation and entropy production are related in master equations. And in the reference 6, on which this talk is based, I've studied this for the Fokker-Planck equation. And in particular, a question that is for me interesting is, what if these relaxation dynamics can only be observed at the approximate coarse-grained level of a single scalar observable? That means instead of looking at the whole relaxation dynamics of the density, let's say that we can access only one or some observables. Okay, the results, just to summarize what I'm going to show briefly, is I found this integral relation which formalizes non-equilibrium impact on the short time scales relaxation dynamics of the Kullback-Leibler divergence. So meaning I take the Kullback-Leibler divergence as the particular observable, and then I study its relaxation dynamics and find an integral relation which relates it to the non-equilibrium currents. And from this, as usual, from the Cauchy-Schwarz inequality, some thermodynamic bounds follow. Okay, the machinery, the usual tools that we use is the small perturbation regime, which means when defining a perturbation field around the steady state in this form, can be shown that when the perturbation intensity is uniformly vanishing, there is an effective dynamics that can be written, basically an effective Fokker-Planck equation close to the steady state. And looking at this, okay, the superscript star means quantities which are evaluated at the steady state. So this means that if we were able to measure the left-hand side of this, as I was saying, basically, we would immediately be able to measure, dissipation, the non-equilibrium currents, and entropy production. But again, let's say that instead we can only have a look at one scalar observable, which, in this case, I've chosen the Kullback-Leibler divergence, which close to a steady state is just the expectation of the squared field, which looks kind of the simplest possible observable here, as the expectation of the field is just zero given by normalization. Okay, and I would say the main results are contained in this slide. Okay, the first is just stability analysis, basically checking that, when I perturb the system from the steady state, it actually goes back to the steady state. Okay, and this is given by this first inequality. But this first inequality is just the Prigogine criterion for stability, and it doesn't tell us much about the non-equilibrium currents, which are this nu star. And well, if instead we look at the second time derivative, we find those. And these are short time scales expansions. Indeed, kind of the second time derivative, we are basically looking at the short time scale, the shorter time scales. And if I isolate the non-equilibrium impact, that means subtracting from the second derivative the equilibrium counterpart, we only have this functional which involves projections of the non-equilibrium currents, this nu star projection, into the perturbation gradients. And as usual, the question is, how do we extract the entropy production from this? And the answer is in the Cauchy-Schwarz inequality, which gives a typical lower bound on dissipation, given by a property of relaxation on short time scales in this case. And also on the denominator, we have this property of the perturbation field. And the thing is that this is rather difficult probably to estimate experimentally this functional of the perturbation. So I was thinking, let us simplify matters by considering particular perturbation fields and ensemble averaging. And here I've added, so majorization and averaging do not commute, meaning that what I'm going to show next is not just an application of this equation, but it's rather kind of going back to the integral equality and applying expectations, and only then applying the Cauchy-Schwarz majorization. And I've considered two particular cases for their analytical tractability and interest. In particular, displacement perturbations look kind of a good candidate for experimental applications, while the second one, constant gradient, maybe a bit less for experimental applications, but surely are the easiest analytically for us. And now without going into the details of the math, basically we can find two refined versions of this non-equilibrium relaxation inequality. Okay, here is just to show that this things actually works as expected numerically. On the upper right plot, we have, so the dots are actually simulations of the Fokker-Planck equation, averages of this relaxation quantity. And the dashed line is just to check that the analytical expansion that we are doing for short time scales, it actually works. And the continuous black line is instead the bound given by the entropy production. And for linear systems, as you can imagine, we are also able to do analytical progress. And so one can even ask, like, what is the tightness? How tight is this inequality? And we can have all these curves. Well, for nonlinear cases, we can do only, numerically one sample at a time, let's say. And these have considered like, two possible samples of random distributions, here coming from a 2D cubic polynomial. And we see that there are, let's say, enough nonlinear away from the linear case, and the machinery still works for, it gives an inequality, a thermodynamic bound, which is quite wide, that's for sure. You can see that the dashed line still kind of fits the data, meaning that the expansion still works for nonlinear systems as expected. And this is all for myself, like more details of course in the paper. And are there questions?